Hello everybody, Mr. Hill here, and today we're going to be talking about working with moles, molar mass, and Avogadro's number. And we're going to use these techniques to help us solve some basic chemistry problems. So the one thing that you're going to have to remember as you work through these problems is that the key component of all of these problems is the number of moles of anything that you're working with. So in class you've talked about what a mole is, that it's 6.02 times 10 to the 23rd of anything, in this case usually particles or atoms. And the reason why this is important is because moles are central to all the conversions and calculations you're going to be doing in chemistry. So from moles, it's very easy to go to the mass of a compound, and it's also very easy to go to the number of particles of a compound or of a particular atom in a compound. So if we're going from the number of moles to mass, we're going to be using the molar mass in order to do that, and we do it through multiplication if we're going from moles. And also if we're going from moles to particles, we're going to be multiplying by Avogadro's number, which is 6.02 times 10 to the 23rd. Now if we had to go reverse the directions of the arrows in any case, then you probably figured that instead of multiplying by those amounts, we're going to end up dividing, which is true. But I'm also going to take you through the step-by-step conversion process that we use to help us make sense of all of these processes so that we know we're doing the right thing. So let's take a look at our first example. So our first example says how many grams of calcium chloride are in 1.35 moles of the compound. So first thing I realize is that we are going from the number of moles, 1.35, to the mass of the compound, and we know that because it's asking for grams. So whenever that's the case, we're going to need to find our molar masses. Now, I like to have a dynamic periodic table on hand, and you can go to ptable.com and you can get one of these. This is pretty nice, has lots of information. I immediately see that calcium is one of the elements that are involved here, so I'm going to have to find the molar mass of calcium, and here I can see that it says 40.078. So we're going to be using a periodic table for the information that we're doing here. So in this case, we're going to keep track of the molar masses of our compound. So we just saw that calcium is 40.078. I'm going to make it 40.1 because I have three significant figures in my problem up here. So I'm going to round this to three significant figures for the molar mass. So calcium's molar mass is 40.1 and chlorine's molar mass is 35.5. But the one thing we have to be mindful of is that there's actually two atoms of chlorine in every molecule of calcium chloride, which means technically to find the molar mass for this compound, I need to multiply the molar mass of chlorine by 2, which is 71.0. So 1 mole of calcium chloride has a total mass of 111.1 grams. So we're going to end up using that to solve the problem. So to go through the systematic process, we take what we start with, which is 1.35 moles of calcium chloride. And I'm going to multiply that by the ratio of 111.1 grams of calcium chloride per 1 mole of calcium chloride. Now I get this conversion because the molar mass of calcium chloride, 1 mole, is 111.1 grams. We found that over here. And I need to do it in this order because I want my mole units to cancel, so numerator here, denominator here, and I'll only be left with grams. And as we saw before, if we're going from moles to grams, we end up multiplying by this number. So to actually do the computation, I'm going to get out a calculator here. And let me see if I can move that out of the way. And my calculation is 1.35 times 111.1. And we can see that it's 149.985. I want to make sure there's three significant digits in my final answer. So I'm going to say there's 150 with a decimal point to make sure that that's zero significant grams calcium chloride. So that is our final answer, 150 grams calcium chloride. So this is a similar situation, but you should be able to see what's a little different about it. How many moles of sodium hydroxide are in 25.0 grams of a sample? So in this case, very similar to last time, but we are going from mass to the number of moles. And recall that that's actually the reverse of what we did last time. So you can probably figure out that we're going to end up dividing instead of multiplying. And that's in fact true. Using a periodic table, I'm going to again find our molar masses. So sodium's molar mass is 23.0 grams per mole. Oxygen's molar mass is 16.0 grams per mole. That's one you should probably have memorized by the end of this course. It comes up so often. And hydrogen's an easy one, 1 gram per mole. So setting up our problem here, we have a total of 40.0 grams per mole of our compound. And we're going to use that knowing that we're starting with 25.0 grams of sodium hydroxide. And my ratio is now 1 mole of sodium hydroxide per 40 grams of sodium hydroxide. Again, the grams start in numerator here, so they have to be in the denominator in my conversion, so I'll only be left with moles. And that means I'm going to end up dividing these quantities. Taking out my calculator again, I'm going to do 25.0, and I'm dividing that by 40.0. And we get that there's 0.625 moles of sodium hydroxide in this in our sample. Now something a little different still. So now this says how many oxygen atoms are in 3.15 moles of tin 4 oxide, or if you just want to say tin oxide for now, that's fine. Here we're going from moles to particles. We're given 3.15 moles, and we're going to how many particles we have. So if you recall from our second slide, that's going to end up being multiplication. And I don't need to worry about molar mass here because I'm not going from moles to grams or vice versa. So this is a little more straightforward. I don't have to really go to my periodic table for anything here. All I need to know is that we're starting with 3.15 moles of tin 4 oxide, and we're going to end up using our Avogadro's number here, so we're going to do 6.02 times 10 to the 23 molecules. It's going to be 1 mole of tin 4 oxide, and that is going to be our universal conversion. If we're ever going from moles to molecules or particles, it's always 6.02 times 10 to the 23rd, because that's what a mole is. It doesn't matter what your compound actually consists of. So the other thing we have to be careful of here is technically we're looking for oxygen atoms, and every molecule of our compound actually contains 2 oxygen atoms. So I need to be careful to make sure I account for that. So for every molecule of my compound, I have 2 atoms of oxygen. This finally will leave me with atoms of oxygen, which is what I want. So I'm going to again take out my calculator, try to get it a little bit out of the way here. And I'm going to start with 3.15, and I'm going to multiply by 6.02. And I like to use, if I'm just doing fast computations, I like to use the EE notation on my calculator for scientific notation. And that makes it so I actually don't need to use parentheses when I'm doing this number. If you do times 10 to the, you might need to use parentheses depending on what you're doing. And then times 2. And this tells me that I'm going to end up with 3.79 times 10 to the 24th atoms of oxygen. So going back, we end up, oops, too far, we end up with 3.79 times 10 to the 24th atoms of oxygen. So now for our last problem. What is the mass of 1.2 times 10 to the 25th molecules of carbon monoxide? So you should be able at this point to figure out what is the most different about this problem compared to all the previous ones. In each of the previous problems, there really was only one conversion that we were doing. We went from either moles to grams or vice versa, or from moles to particles or vice versa. But in this case, we're actually going from particles, since we're given 1.2 times 10 to the 25th molecules, to moles, and then to mass, because that's the question. So this is actually a double conversion. And from particles to moles, we're going to need our Avogadro's number, 6.02 times 10 to the 23rd. And as always, when we go from moles to mass, we're going to need our molar mass. So anytime we need molar mass, we should start by finding the molar mass of the compound in question. So let's get our molar masses ready. So I know that carbon, looking at my periodic table, is a molar mass of 12.0 grams per mole. And oxygen, as we saw before, is 16.0 grams per mole. So the total molar mass of carbon monoxide is 20.0 grams per mole. So what are we starting with? We're starting with the 1.2 times 10 to the 25th molecules of carbon monoxide. So let's get that going here. And our first conversion is to go from particles to moles. So again, recall that since molecules are up top here, they're going to end up on the bottom in our conversion. So 1 mole of carbon monoxide is equal to 6.02 times 10 to the 23rd molecules. Now that we have a mole of carbon monoxide in the numerator, we're going to multiply that by our molar mass, 20.0 grams of carbon monoxide per 1 mole. So you should be able to see what's going to happen here with the conversions. The molecules cancel out, the moles here cancel out, and the only unit left is grams, which is exactly what we want because it asks for mass. So again, we're going to bring out the calculator, and we're going to now do the computation. A bit more computation here, but not much. So 1.2. Again, I prefer to use my double E notation for scientific notation on the calculator. It makes some of the computation a little easier. So 1.2 times 10 to the 25th. Some students like to multiply by the 1 when they do this. I don't do that because multiplying by 1 doesn't change a result. So I skip the 1s if you haven't noticed yet. If you like to multiply by the 1 and then divide, it doesn't really matter. So I'm just going to divide then by 6.02 and use my scientific notation here, times 10 to the 23rd, and then multiply that value by 28.0. Now notice when I use the E notation here in my calculator for scientific notation, I don't actually need to use parentheses. That's one of my favorite things about doing it this way. That makes it a lot faster. Now some students just like to use parentheses anyway around each of these numbers, and that's fine. It's just not needed if you use the E notation on the calculator. Again, if you use the times 10 to the, if you literally multiply 1.2 times 10 to the and then divide, you'll need parentheses when you divide by a number like that. But anyway, let's see what this gives us. This gives us 558.139 grams. So looking back at my original problem, I see there are 2 significant figures, so I only want 2 significant figures in my result. So that means I'm going to have to only have the 5 and 1 more digit, so I'm going to round that up to 6. So totally we're going to have 560 grams of carbon monoxide. So I hope these examples have shown you how you can use molar mass, Avogadro's number, and just the mass of compounds in order to solve some basic chemistry problems. And always remember that moles are your center point. So you're almost always going to end up finding the number of moles of something if you haven't been given it already. If you have been given moles, it's a great start because it goes very easily to other units. So there you go. I hope you've enjoyed this, and I hope you have a good day.